Hello and welcome to this video, chapter topic 15.2, Entropy and Spontaneity. This is part 1 of this chapter, so we're going to focus on the entropy part in topic 15.2. We will start with the essential ID for this topic. In the essential ID we can read that a reaction is spontaneous if the overall transformation leads to an increase in the total entropy. The direction of spontaneous changes always increases the total entropy of the universe at the expense of energy available to do useful work. And this is known as the second law of thermodynamics. So we're going to actually look at two different things here. We're going to look at the term entropy, and we're going to talk about that, and we're also going to do some applications with calculations. Gibbs free energy is one thing that we're going to focus on. So this was the essential ID. If we now take a look to the understandings and application in skills in your chemistry syllabus, the entropy is what we're going to focus on today. The entropy sign for the entropy is S. And the unit for entropy is joule per Kelvin per mole. You can see here also. So entropy is a measurement in which the available energy of a system can be distributed among the particles in the system. And when you think about the term entropy, one thing that you can have in mind is like if you think about your room at home. It can by itself spontaneously get messy, and in order to bring order, clean, you have to put in energy. So the entropy is a kind of a measurement of how disordered the entropy is, like the room of disorder, and how you can see the particles were like distributed in the system. So if we take a look at this picture, maybe it's even clearer. If you have a high entropy, you have a lot of disorder, and you have this kind of, if the particles are in a system. If you have a high order, this is a small entropy. So say that this is your clean room, and then it gets more and more messy, and the entropy will increase. So a disordered system means a high entropy. So we're now going to focus and apply this to the chemistry. And one thing is that I want you to know is equation of how you can calculate the delta S, and that is the measurement of entropy. And we're going to look at the products and reactants. So just write this equation. I will show you soon how to apply it and which kind of exercise it is suitable. For example, of different positive value, because if you have a positive value of delta S, it means that the entropy will increase. So a positive value of delta S means increase in entropy. One example is if you mix in different types of particles. So if we state this is 1, this is 2, this is 3. And I will give you some real example also. So for the first one here, if you're mixing different types of particles, that is one way we can see the entropy will increase. For example, if we dissolve salt in water. That is one way to increase the entropy for this system. So sodium chloride will put into water in liquid state, and what will happen is that these particles will divide into aqueous state and ions and water. So this is one way to increase the entropy by mixing different type of particles and make them into a more disordered system. The second one here says that if you want to have a positive value of delta S and an entropy that's increasing, you can do that by the distance between the particles when you change state. Clear example of this can be when you boil water. when you get liquid state and you transform it to gaseous state. So think of this picture again. This is water, and what will happen when we heat it up? Well, it will boil and go into gaseous state, and that will spread them out, so the entropy will increase in this way. The third one here was the increase in the movement of particles. One example here. 3. And in this case it can be, for example, if you increase the temperature of a liquid or gas. So this is really connected to the second one here, where you can see that increasing a temperature will also do the effect that the entropy will increase. And the fourth one here, increasing number of particles. This is also one way to increase the entropy. Example can be this one here. We divide to wrote wrong here. So P cell free, and then you have these two. So here you have one on this side, and you have 2 particles on this side. So that is also one way you can increase the temperature, and you can assume that the delta S value will be positive. So now we're going to an exercise. In this exercise, they want you to identify which of the changes of this one here, you have 6 different, will have a negative value of delta S, and which will have the positive value. So you want to, one by one now, go through, and you can think about what I just told you about the factors that will affect the entropy to increase. It means that if it doesn't do that, we can expect it to decrease. So positive value of a delta S means entropy will increase. So we can take the first one here. In this case, you see we have aqueous state to solid state, but we can also see that we have a decreasing in number of particles. We have 2 particles on this side, and we have 1 on this side. And also we can see that we get to a more ordered state. Aqueous state is more disordered than the solid state. So just by looking at the kind of state, aqueous state is more spread out than if you have it as a solid, and also we can see that we have 2 here and 1 here. So the entropy is actually not increasing, it's decreasing. Decreasing entropy means that the negative value of delta S. So yes, for A we can expect the delta S to be negative because we can see a decrease in entropy. Okay, we take the next one here, B. Here we have gaseous state for them all, so we have the same kind of state. What we can do here, we can count the number of particles. We have 4 particles on this side, 1 here and 3 here, and we have 2 here. So we can see that we go from high number of particles to a lower number of particles, and in that way we know that the entropy will decrease, so the delta S will be negative. This one here, you have mercury in liquid state that will transform to mercury in gaseous state. The transformation is from a high ordered kind of state to a more disordered kind of state. Liquid is more ordered than the gaseous state. So we can expect it go from a more order to a higher disorder. So entropy will increase, delta S will be positive. And then we take D. Here we have another thing we need to take into account. We have solid state here and aqueous state here. And we can see that this actually belongs together, and we have this is solid state, so it's an ionic compound. So it's ordered to a more disordered kind of state. it means that we have an increase in entropy. We're spreading out. Delta S will be positive. We go to this one here. In this case, you want to count the number of particles. We have 5, 6, and we have 7 on this side. So we can see we go from 6 particles to 7 particles. It means that we have an entropy that is increasing. More disorder, delta S will be positive. And the last one. We have solid here. We have different kind of states. But for example, we have solid go to aqueous. So we have gaseous also here. So we can see that we have more ordered kind of state here than we have here. And also we have 3 particles here, and we have 2 here. So there are 2 different evidence of saying that there actually will be more disorder. So we can see that delta S will be positive. So both of them, we can see that it's more disordered here, and that is why we can do it like this. That was the exercise. The next exercise will be of the calculations of entropy. I will show you how to deal with that. So this is the exercise, and once again I want to remind you of the equation that I just briefly showed you. I will write it here. Delta S for the reaction, the entropy for the reaction, is equal to the entropy for the products minus the delta S value for the reactants. So this is the equation you need to have with you when you are calculating the entropy for a reaction. So in this case you also have stated the different values here. You have the standard entropy for oxygen, sulfur dioxide and sulfur trioxide are respectively 205 for oxygen, 248 for sulfur dioxide, and 256 for sulfur trioxide. Calculate the standard entropy change for the reaction. My recommendation is that you take products for itself and reactants for itself. So this side of the reaction arrow is the reactants, and this is the product. So entropy for reactant, well, you have sulfur dioxide, that's 248, and you can see we have 2 of them, so we need to multiply by 2. And then we have 1 oxygen, 205. Put that in your GDC. 248 times 2 plus 205, 701. And you can see the units here, joule per Kelvin per mole. And then you do the same for the products. And it's sulfur trioxide, 256 from the information we have in the exercise here. And we can see we have 2 of them, so we need to multiply by 2. And that will be 512 joule per Kelvin per mole. Okay, now we have stated the final entropy for both the reactants and products. Now we're going to use the equation to calculate the delta S for the reaction. So we take the products, 512, minus the reactants, 701. minus 701 minus 189. So we can see we have a negative sign for the delta S of the reaction. It means that we have a negative value for delta S for the reaction. We can expect the entropy to decreasing. It means it goes from a disorder to a more ordered kind of system. Yes, so this was the first part of chapter 15.2. Next chapter will be application of Gibbs free energy and some other things. Thank you for watching.